This is the last lecture from chapter 16 about acids and bases, and I think of it kind of as a catch-all. So it's all the topics that maybe don't have enough content to take up their own lecture, but it's something you should be aware of. And that's polyprotic acids, and that's just basically you understanding that they exist, and they are compounds with more than one acidic hydrogen. And then Lewis acids and bases, that is a different, even more broad definition of acids and bases than the Bronsted-Lowry one. And finally, the fact that salts, which is kind of the nickname for ionic compounds, can actually make an aqueous solution acidic or basic, some of them. If you have a carbonic acid, so let's just say phosphoric acid, and you put it in water, the ionization is going to happen in steps. So in other words, the first hydrogen ion will be donated to the water, and oh boy, I got myself too cramped here, didn't I? And the Ka for this first release of the first hydrogen is called Ka1. And then in a second step, once you have the conjugate base from the first ionization, it can donate its second and then its third. And each of the subsequent hydrogen ion donations have their own equilibrium value, and it gets progressively more and more difficult, requires more energy to remove each hydrogen ion. In general, the difference between the equilibrium constant values for successive ionizations is huge, at least usually 3 orders of magnitude. So it's most of the time very safe to only look at the first ionization value and ignore the second and or third one if there is, except for sulfuric acid. So sulfuric acid, even the second ionization constant is quite strong. And so you'll see in chemical reactions, for the most part, people treat, when they're writing out a balanced reaction for sulfuric acid in water, they will usually just remove both of the hydrogens. Here, my puppy. So normally you'll just see both hydrogens snatched off because they're both pretty easy to do. All right, Lewis acid base definition. While Bronsted-Lowry is the most common, most popularly used, Lewis acid base theory does have some good use. And Lewis acid base theory focuses on the transfer of an electron pair instead of the transfer of a hydrogen ion. Now you'll see in the next couple slides that a Bronsted-Lowry base is always a Lewis base also, not so for the acid. But a Lewis acid does not require having hydrogen atoms as a Bronsted-Lowry acid does. All right, so the electron pair donor is the Lewis base. And I remember this as a student because to me it seems the opposite. If you're talking about Bronsted-Lowry definition, you kind of think of the base as the acceptor, right? The proton acceptor. Well, it is a proton acceptor, but it's also an electron pair donor. Those are not mutually exclusive. So the Lewis base must have a lone pair of electrons. The electron acceptor is called the Lewis acid. So in order to be a Lewis acid, you have to have something that's electron deficient. All right, so here's a typical example of a Lewis acid-base reaction. So hopefully you know by now that ammonia is a weak base from the Bronsted-Lowry definition. It has a lone pair of electrons, so it can also serve as a Lewis base. What's different in this reaction, however, is we would never classify boron trifluoride as a Bronsted-Lowry acid because it has no hydrogen to donate, but it can accept an electron pair, and usually that electron pair is used to make a bond between the Lewis acid and base. And so a Lewis acid is not always a Bronsted-Lowry acid. In order to be a Lewis acid, as I said before, it must be electron deficient in some way. So if you see anything with a positive charge, that means it's electron deficient. If you see something with an incomplete octet, such as boron, only has 6 valence electrons in a compound, then that is considered electron deficient and would make a good Lewis acid. So as I said in the last slide, the electron pair on the Lewis base is typically used to make a covalent bond with the Lewis acid, and this pictorial just shows that nicely. Here are a couple more examples. If you look at the reaction on the top, this happens to be called an ether. Oxygen, in this case, as usual, has a lone pair of electrons, so it could function as a Lewis base. The reaction it's undergoing now shows that it abstracts a hydrogen ion, and so in this reaction, it is also functioning as a Bronsted-Lowry base because it's a proton acceptor. So as I said before, any Lewis base can also serve as a Bronsted-Lowry base. In this particular case, hydrochloric acid is serving as a Bronsted-Lowry acid because it's donating its hydrogen ion, but it is also serving as a Lewis acid because it is accepting the electron pair. Look at the bottom reaction. Again, it's the one that we went over on the other page, but ammonia can serve as both a Bronsted-Lowry and a Lewis base, but if you have a Lewis acid that does not have a hydrogen ion, that is just a Lewis acid. So just to kind of give you a better feel, because I know it seems like a rather abstract concept. So again, Lewis bases have to have lone pairs of electrons. Clearly, if you have a minus charge on a substance, there's a lone pair of electrons available. Lewis acids are electron deficient, so either compounds that have an incomplete octet, quite often, well, both of these have an incomplete octet. Quite often, if you have metal cations in a compound, they will function as a Lewis acid. Or really, anytime you see a positive charge, you have an electron deficient species, but it doesn't have to be positive charge to be a Lewis acid. All right, the pH of salts is clearly the most complex topic in this particular lecture. So first of all, remember that when chemists say salt, it's a generic catch-all phrase for ionic compounds. And just as a reminder, when you have an ionic compound that's soluble in water, what it does immediately upon, well, actually what the process of dissolving is that the ionic compound dissociates, you can call ionization also, into the cation and anion. And sometimes those cation and anions cause the solution to be acidic or basic. What's challenging when you're dealing with the acidity of salts is you have to, in order to determine whether or not they make a solution acidic or basic, you have to kind of think backwards and where the cation or anion was derived, and that can get tricky. So this may not make sense for the next couple slides, but hang in there, and I think it ultimately will make sense. So if you have a cation that comes from a weak base, so for example, the ammonium cation came from the neutral compound ammonia, which is a weak base. So if your cation comes from a weak base, they can make the solution, or will make the solution, slightly acidic. If you have an anion from a weak acid, so if you're asking yourself, what is the acid that fluoride ion could come from, it'd be hydrofluoric acid. That is a weak acid. So if an anion comes from a weak acid, it will make the solution slightly basic. I just realized I did not balance my reaction on top, did I? There we go. All right, and you can see that because of the byproduct of each of them is either an OH or a hydronium ion. One thing I want you to remember at this point from this slide, even if you don't understand the concept yet, is that cations, if they're going to change the pH, will make the solution acidic. Anions, again, if they're going to change the pH, will make the solution basic. It's just an important concept. So on the last slide, I talked about cations and anions from weak acids or bases. So now let's look at cations and anions that come from strong acids or bases. If you decide they are from a strong acid or base, they do not affect the pH. So let's look at table salt, sodium chloride. That is soluble. If we add it to a solution of water, because it's soluble, it will immediately dissociate into the cation and anion. And now, if you're trying to decide whether a salt, in this case sodium chloride, will affect the pH of an aqueous solution, you need to treat each ion that forms from it, decide whether they come from a strong or a weak acid or a base, and then determine the effect on the pH. So we're going to start with the chloride ion, okay? Chloride ion comes from HCl. That is a strong acid, okay? Which means chloride ion cannot have any effect, or does not have any effect, on the pH. Sodium cation, likewise, comes from sodium hydroxide, which is also a strong base, and so the sodium cation has no effect on the pH of a solution. So if you determine they come from a strong acid or base, it ends up being a neutral salt solution. Here's another example. All nitrates, well, it's nitrite, but that is soluble, has a metal from group 1A, and that automatically makes the salt soluble, just kind of reminding you of your solubility rules. And so upon putting in water, it would immediately dissolve and dissociate into the cation and anion. You would need to analyze each of these ions to see if they come from a strong acid or a base. So the bottom line is, if you haven't already picked this up, all you do from the anion to see where it came from is add a hydrogen ion to it. And so NO2 minus, that's nitrite ion, comes from HNO2. That is a weak acid. This is one that can get a little tricky because HNO3, nitric acid, is strong. So got to pay attention to your subscripts. So because it's from a weak acid, it is capable of affecting the pH of a solution to make it basic. The potassium ion, and to see where a cation comes from, just stick an OH on it, okay? So it comes from KOH. That is a strong base, so there'll be no effect on the pH from the potassium ion. So let's look a little closer at the nitrite ion and see how it could make a solution somewhat basic. The reason an anion from a weak acid such as nitrite, can make an aqueous solution basic is because when you dump nitrite in water, it is capable to a minor degree of abstracting some of the hydrogen ions from a water molecule. What are the products when it does that? The original intact acid, but it has also produced some free hydroxide, which means this overall solution will be basic. Now, this is not going to happen a lot, but it clearly is capable of happening. Here's a list of the steps that you need to go through in order to determine whether a soluble salt can affect the pH of a solution. So you may want to jot these down. The first thing you want to do is dissociate into the cation and anion. The second is determine whether each of the ions, whether the cation and the anion, come from a strong or a weak acid and base. Just to kind of help you out here, to determine where a cation comes from, just kind of stick hydroxides on it, right? And then ask yourself, is that weak or strong? Anions, just add a hydrogen ion, and again ask yourself, is that weak or strong? So if either one of them comes from a weak acid or a weak base, you have to go a step further and write the reaction between the cation or anion that comes from a weak acid or base. Write out the reaction, what would it do in the presence of water, what would it form, and that will show you how it makes a solution either acidic or basic. Now, if you're asked a quantitative question, like what is the pH of the solution with a particular cation or anion, you need an ice table because these are equilibrium. All right, so here's an actual problem. Determine the pH of a 0.59 molar solution of, this is called sodium acetate, which you don't need to know the name of necessarily. So the first thing you should work out in your head is, okay, this is a salt. How do I know that? Because it has a metal and a polyatomic ion. It has a metal in it, so that's an ionic compound. You're probably more used to seeing this with sodium in the beginning. I don't know why I put it at the end there. All right, and they gave you the Ka of the acid from it, okay? All right, so remember my steps. First thing you do is separate it into the cation and the anion, all right? Remember the metal's always the cation. Then you have to ask yourself, where are each of these ions from? So remember, if you're looking at the anion, you simply want to add a hydrogen, okay? So acetate is from acetic acid, which is a weak acid. So this acid here can, in fact, change the pH, okay? Sodium cation, on the other hand, when you're looking at the cations to see where they came from, just put a OH on them. So sodium cation comes from sodium hydroxide. That is a strong base. If they come from strong acids or base, they have no effect on the pH. So we really just have to go a step further with the acetate ion and see what it's going to do to the pH. So again, if you have an ion that comes from a weak acid or base, as acetate does, you then should write out the equilibrium between that ion and water. Anions can act as weak bases. So when acetate ion reacts with water, you're going to get some acetic acid, and what's left over is the hydroxide. So remember, the anions, if they affect the pH, are going to make it basic because they produce hydroxides. Since this is serving as a base, we need Kb. This is one of the instances where the problem pretty much deliberately tricked you. It gave you Ka. So in this case, you need to convert from Kb to Ka. So that's the Kw value divided by the one you don't want. and here's our Kb. I love when the K values are the value of 10 to the minus 4 or more negative, because that means we're going to be able to neglect X in our ice table. So here's the ice table. Here's the equilibrium that's occurring. Ignore water, it's a liquid. The problem gave us the initial concentration of the acetate ion. And so we have to use X. We can neglect this X because K was so small. Now it's simply a matter of plugging and chugging. Here's our expression for Kb. Remember that Kb has hydroxide in the numerator. They gave us, or well, we had to calculate the value for Kb. Here is the values plugged in, the equilibrium concentration values. We are again going to neglect X because K is so small. And now we just solve for X. Remember, X is going to give us the hydroxide ion concentration. This problem asks us for pH. So first you must find POH by taking the minus log of the hydroxide concentration. And once you get POH, you have to find pH. So it's 14 minus POH. And so our final answer is, if we put sodium acetate, which is an ionic compound, into an aqueous solution, it is going to make that solution basic because the acetate ion, okay? Normally, I don't like these concept maps because they're so complex, but this one I thought was really good. This is an overview of Chapter 16, and it's a good one. It's all the key topics that you should have learned about and that you should know about for acids and bases. Some key definitions, okay? Calculations that involve pH and POH, how we determine the strength of an acid or a base. We use the equilibrium constant. We find pH of strong acid and base in a very simple way, minus log of the concentration. But then we also learned if we have a weak acid or a base, we're dealing with equilibrium constants. And we have to make ice tables if we had weak acids or bases. And finally, salts or ionic compounds can change the pH of water. That is it for this lecture. That's also it for Chapter 16.